We're good. Okay. Professor Erika Hamden is here with us today. Her area is UV instrumentation, detector technology, galaxy evolution, and star formation. She's the PI of a few major programs, and I think she's probably going to talk to you about those today. She got her bachelor's from Harvard, her PhD from Columbia. She did a postdoc at Caltech. She's got way too many awards, major awards to go through all of them, but she's, I was telling her earlier, overachiever is just not a word that would describe everything that she has done. And I've seen her TED Talk, and it's amazing. So we're lucky today to have Professor Hamden.
Thank you. I was saying earlier that this is like the easiest travel I've ever had for a colloquium. But I'm really happy to be here with all of you. And today I'm going to talk about some of my work in the ultraviolet and spend a little time talking about why, as I was also talking about earlier, the ultraviolet is sort of the least utilized wavelength range in astronomy. So I'm going to start with actually just a very brief history of ultraviolet missions. The UV has been, as soon as people realized that you could put a telescope in space, there was a realization that, we should put a telescope in space and have it observe in the ultraviolet because the atmosphere blocks all of the ultraviolet, which is good for life on Earth, but it is bad for UV astronomy. So the very earliest telescopes were actually going up in the 60s and 70s. There was a really early space telescope called Orbiting Astronomical Observatory, OAO. Number 1 didn't work. Number 2 was a UV telescope that discovered that galaxies were bright in the ultraviolet. In 1970, there was a suborbital rocket which discovered the presence of molecular hydrogen in the interstellar medium, so the stuff between stars. Molecular hydrogen is the most abundant molecule in the universe, and the PI of this was a really interesting astronomer named George Carruthers. This paper on this suborbital rocket is a single author paper that he wrote. He built the whole thing, launched it. I guess you could do that in the 70s. And he was actually also a really innovative inventor. So he invented certain UV spectrographs, one of which ended up on the moon on Apollo 16. And this is some data from that spectrograph. So this is looking at the Large Magellanic Cloud. And the spectra are going in this direction. And then since the 70s, there's been other missions. FUSE is one that is a model for a mission that I'm going to talk about later, looking at universal deuterium. The Hubble Space Telescope has a UV channel and looks at basically everything. And then more recently, there was a large field of view imager called GALEX that studied galaxy evolution. But if you made this list for almost any other wavelength, it would have 100 missions on it. And here in the UV, we have a little over 10. And so why is the UV this critically undersampled part of astronomy? And so this is a table from a colleague at CU Boulder, just showing the percent of sky coverage in different wave bands. So you have gamma ray, X-ray, and the very extreme UV, which is sort of like soft X-ray. And your sky coverage is 100%. On the other side of this, radio, actually not a full 100% sky coverage, but all bands of the infrared and the visible have 100% sky coverage. And then the UV, the near UV has 70%, the far UV 70%, and then this Lyman continuum UV between 912 and 1200 angstroms is less than 0.03%. That's not a typo. There's just been barely any part of the sky covered in it. These 70%, has been observed at all. Yeah. So this 70% of the sky is from GALEX, which did an all-sky survey, but GALEX, the detector that it used, could not look at bright objects, so it wasn't able to observe the galactic plane or any interesting bright objects in the galaxy. So the 30% of the brightest stuff is what's missing from the far UV and near UV channels. So this figure I always show because I have a real axe to grind as a UV astronomer. And I thought about this a while. I started working in the UV in 2008, and so since then I've been wondering, why is the UV this forgotten wavelength range? And I have a few theories about it, none of which I think are that great, but maybe combined they work together. So one of them is the obvious that Atmospheric transmission is bad in the UV, so you have to be above the atmosphere in orbit or maybe on a stratospheric balloon. But the atmospheric transmission is also bad in the X-ray and in the infrared, and there's tons of telescopes in those band passes. So I feel like that alone is not the reason. The materials that we work with can be difficult, so most substances that are great in the visible, you can make your mirrors out of aluminum with like maybe a very thin mag fluoride coating. Those mirrors lose their reflectance the farther into the UV you go. Or you might be using fibers for something, and those fibers work great at certain wavelengths, and then when you put them in the UV light actually destroys the fiber and reduces the transmission over time. So there's a lot of stuff where the UV, it's powerful enough to cause problems. The photons have enough energy to cause problems, but they're not so powerful that they're like X-rays where they can like bust through anything. So they typically get absorbed and they destroy your system over time. The other reason might be a lack of military or commercial or ground-based applications, because if I build a UV telescope or a UV sensor and I want to use it on the surface of the Earth, I'm not going to see very much. And so there isn't something like the infrared where you can use infrared detectors for a lot of other uses. And so potentially all of these things combined to make it a little bit harder than other wavelengths, which is kind of annoying because the UV is incredibly valuable scientifically. Sometimes when I like to get a rise out of infrared astronomers, I tell them that all of extragalactic astronomy is just looking at UV photons that have been redshifted into the infrared. And they hate it, but also it's true. So for the next couple of slides, I'm just going to talk about a couple of different scientific applications in the ultraviolet. One of them is looking at the stuff around galaxies. So the regions around galaxies are called the circum-galactic medium. It's the stuff, the medium around the galaxy. And the circum-galactic medium we know is full of material. It's not in stars, but it's like atoms of hydrogen or oxygen or whatever. And it has different temperatures, and it's like actually a very complicated place. But our observations of it are really limited. So this figure is showing the density and temperature from a simulation and all these different elements that are traced at different densities and temperatures. So one element that I'm going to talk about later is oxygen 6, which is like hanging out over here, that traces a pretty well-populated area at an intermediate temperature and a low-ish density. So each of these elements corresponds to a line on this plot, which is showing the observed wavelength and then the redshift at the top, or you can think of this as look-back time. If you're looking at a distant galaxy, you're looking in the past. And all of these elements that are excellent tracers of the circumgalactic medium, all of them except for one, have their rest frame emission in the ultraviolet. And if you want to observe them from the ground, you have to observe them in high redshift galaxies, where you're looking at redshifts of 2 or greater. And if you think about this in terms of time, you're looking at galaxies that are 10 billion years old or older. And so if you're interested in what is happening in the universe now, in the halos of galaxies, or even 5 billion years ago, you have to have a telescope that can actually observe in space to look at these tracers in the space ultraviolet. So there's a few missions, Aspera, which I'll talk about later, Fireball, which I'll also talk about later, and then some others that are working on trying to do this from space. Then there's also exoplanet science, which is extremely popular right now. And this is both observing the planet itself and the host star around which the planet is orbiting. So depending on the type of star, you could have a planet that you think is rocky, that might be like an Earth mass planet, on a potentially in an orbit that puts it in the habitable zone of its star, which is where we think there would be liquid water on the surface if the planet has an atmosphere. But, so that could all be true, and you think, great, this is a planet that could have life, let's spend a ton of resources to investigate it. But if you don't know what is happening in the star in the ultraviolet, you're going to waste all your time, because there are lots of stars which are extremely bursty in the UV, where they will like have a flare and put out a ton of energy and basically sterilize the surface of any planets that are within a certain distance. So you could have a perfect planet, except that the star is super bright or variable in the UV, and that every, 1,000 to 10,000 years, the planet gets irradiated. That planet is not going to make any cells or anything. So you should carefully select your targets for follow-up. So this figure is just showing kind of how an active or inactive star can change the atmospheric signature of a planet that is orbiting that star, and then also how something like the Earth has a really clearly different signature in the visible than into the ultraviolet because of the presence of oxygen in the atmosphere. And so observing both the atmosphere of the star or of the planet and the behavior of the host star in the UV, you can figure out whether it might have life or not. Another really interesting and new topic that the UV is important for is multi-messenger astrophysics, which is a fancy way of saying gravitational wave follow-up. So when you have two neutron stars that merge, they send out a bunch of gravitational waves. LIGO picks it up. Maybe LIGO and Virgo pick it up. And if you can get the localization and figure out where that neutron star merger happened, you can then also look at the optical signature of that merger. So you get gravitational wave information and you get photon information, so that's why it's multi-messenger. So this is an example from the first neutron star merger that was captured in 2017. And you can see how the light curve, so this is flux on the y-axis and then the wavelength range, the x-axis. So it was first caught like a little after 1 day after the merger. Swift was able to observe it just briefly. And over time, it cools off pretty quickly. So that's why you see this, the overall dimming, and the peak of this emission is shifting into the red. But HST wasn't able to observe it until 5.5 days after the merger happened. But we think that these mergers are super bright in the UV, and there's a ton of information about what gets formed and the abundances if you can catch the spectrum in the UV early on before it starts to cool off so much that you basically have a flat line here. So multi-messenger astrophysics, there's a couple of different missions that are in development to try and have like really fast follow-up with UV information. And there's others, but I'm not going to get into all of them because, as I said before, it's really all of astronomy. It should be UV astronomy. There's other things like large-scale structure, star formation, studies of the interstellar medium of our own galaxy. And the other thing that really is both good and really annoying is that the UV is actually, if you take away all the technical challenges, just from like a pure observing standpoint, it is a really beautiful wavelength to observe in because the sky backgrounds are really low. So when you're taking data on the sky, you have to deal with the noise from your source. There's always going to be some inherent noise in it, but there's also noise from other things. There's noise from your detectors, sure, but there's noise from the sky. And if you're on the ground, that sort of sky background is a function of the altitude that you're at, like sort of the level of cloud cover. Is it a humid day? You get just reflection off of humidity in the atmosphere. But if you go to space, of course, the sky background is lower, but it's not zero. And in the visible, your sky background is dominated by light from the Earth, the Earth shine, and zodiacal light, which is light. It's sunlight that is reflected off of the dust left over from the formation of the solar system. So there's like a plane of dust. Depending on where you're looking, you can get this signature of zodiacal light. So these two figures are from the HST handbook, and they're showing different wavelengths and intensities. This is a log scale, and this is just a not log scale, showing the contributions of different Earth shine, zodiacal light, some of these air glow lines here. And as you go from the visible into the ultraviolet, depending on how far into the ultraviolet you go, you get like several orders of magnitude lower sky background. So here in the far UV, you can look at really faint objects, and they're still above the sky background. So you can do, that's partly why you can do observations of the sort of halos of galaxies, because that light is so faint, but the sky background is even fainter. So part of my mission as a scientist is to fill in that table so that it's 100% coverage in at least the near UV and the far UV. And also kind of encourage people to not just view the UV as this annoying wavelength range that always gets put at the end of the decadal survey acronyms. So the Astro Decadal Survey came out last year, and there was one of the large flagship missions was called LUVOIR, Large UV Visible Infrared Telescope. And then the Decadal didn't want to explicitly endorse LUVOIR, so they changed it to be like, oh, well, there should be a large infrared visible UV telescope. And I'm like mad that they put UV at the end. So hopefully over the course of my career, UV will be at the beginning of things. And it is changing. Things have changed a lot, actually, since I started in 2008. There's been a big increase in the number of people who at least are aware of the fact that there's this gaping hole in astronomy in the ultraviolet, and we need to do something about it. But what has been really important is actually doing technology development, partly because UV is difficult to work in, the technology has lagged behind. The detector technology that we're typically using is the same as that was being used in the 80s. And I'm not really exaggerating that. The mirror technology is now getting a lot better, but it was only because NASA started putting money into basically UV technology development. So I'm going to talk about a couple of different things which have been really important for the missions that I work on, covering reflective surfaces like mirror surfaces, gratings, and then detectors. And detectors I have like a super soft spot in my heart for detectors. So if any of you are interested in detectors and want to talk about them, like please let me know. So the first thing that's been really important is the improvement in UV coatings on mirrors. So there's a group at Goddard that we're working with on one of our missions. This is Manuel Quijada in their coating chamber. And basically the issue with UV mirrors is that historically they are very bad. And the reflectance of fuse, for example, is this dotted blue line here. This goes from 0 to 1, and the fuse reflectance is about 60%. And what this means for optical design, I probably don't have to spell this out for you guys, unlike every other talk that I give, but like if you're losing 40% of your throughput at every bounce, that means that you really need to minimize the number of surfaces in your system. And if you cannot afford more than like 3 surfaces, you're going to have a really hard time dealing with actually making like a nice optical system, because you can't just add another surface in order to reduce your aberrations. You have to just deal with the not great situation that you have. So the lack of good reflectance has meant that most UV space telescopes have very simple designs with like 2 surfaces, or maybe only a few more than that. So the improvement has been this mirror was aluminum with a lithium fluoride overcoat, and part of the reason why the reflection is so low is that lithium fluoride absorbs water really easily. And even if you keep it in like an extremely low humidity environment, it actually absorbs water while it's on the launch pad, and then it also absorbs water that just happens to be like nearby when it's in space. And you would think space is a vacuum, that shouldn't happen, but it's not a perfect vacuum. So the mirrors get worse in space over time. And so one of the things that Manuel Quijada's group developed was actually this advanced lithium fluoride deposition process, where the lithium fluoride that they put on the aluminum, it's done through like heating the substrate to certain temperatures, and you can get much higher reflectance, up to 90% down. So this goes from 100 nanometers to 150 nanometers, so down below Lyman alpha. And this is closer to what the reflection of mirrors is in the visible, where you can put lots of surfaces and you're fine. So this is a huge benefit to new UV missions, that you no longer have to like restrict yourself to just a couple of mirrors.
It was just reducing the porosity of liquid lithium fluoride?
Yeah.
The composition?
It's making it like more stoichiometric, and then reducing the like pinholes and other defects, basically. So then the other like technology developments that are happening is improving UV gratings. And so there's a project that one of my students, Jessica Lee, pictured here, is working on. The PI of the project is actually a collaborator at the University of Iowa, Carrie Hoadley. But UV gratings have also suffered from pretty low efficiencies. If you're just doing like a ruled grating, which has been standard for several hundred years, you get a lot of scatter, and in the UV, that scatter becomes a bigger problem. So this figure is showing the HST gratings here with efficiencies of about 30%, some other mechanically ruled gratings here, and then using a different process that is basically E-beam lithography. So using techniques from photolithography and then E-beam to actually etch your silicon, you can get these like super nice gratings that are really regular and aren't going to have all the defects that are going to cause a lot of scattering, and so potentially have efficiencies that are several times better than the previous state-of-the-art for UV gratings. So this is a big improvement. And then, of course, so you have your mirrors, you have your grating, and then the last part of your optical system is going to be your detector. And so one thing that I've worked on for a really long time is making UV detectors better. And I have worked with a team at JPL on this process that's called delta doping. And so the previous state-of-the-art for UV detectors is a technology that's called a microchannel plate, where you basically have a photocathode that your photon hits the surface, you make cascades of electrons, and it multiplies down as it falls through the microchannel plate, and then there's some type of sensor at the bottom that reads out where this cascade happens. Typically, their efficiencies are pretty low, less than 30%, but in the UV they work, whereas for a regular CCD, which is the standard for detectors in astronomy, the efficiency in the UV is 0%. And that's because the circuits on the front of a CCD, so this is like a cross-sectional area of a CCD here, the circuits on the front are extremely absorbing to UV photons. So if you put UV photons on the front surface, they will be absorbed and you don't get anything in your pixels. Sometime I think in the 90s, people realized that actually if you took the CCD, so these lines here that are labeled FIUV, FIVS, that stands for front illuminated. So people used to illuminate their CCDs from the front, which seems like it makes sense. Someone realized at one point that if you flipped it around and illuminated it from the back, it would actually perform better because you don't have all this circuitry on the front to get in the way of your photons. So back illuminated CCDs have much closer to 100% quantum efficiency, even in the visible, but they still have no quantum efficiency in the UV. And the reason why is because the back surface has these traps and a little potential well. UV photons have a very shallow absorption depth, so they get created in the first couple of nanometers in the silicon once the photon hits the surface, and so they all end up trapped in this little well. If you actually expose it long enough, you'll fill up the well, and then for a little while your CCD will be UV sensitive, but this is not stable. But eventually, if you fill this well up, you can get your photons to go into the pixel, but it's like really difficult to calibrate because your QE is changing all the time. So the process of delta doping, which was developed before I joined the group, is to basically passivate the backside surface using the single atomic layer of boron. So again, this is the cross-section of the CCD. Here's the front. You thin it to about 10 microns. You grow a perfect layer of boron, and then you cap it with more silicon using a molecular beam epitaxy machine that basically perfectly matches the silicon crystal structure. And so this changes the electric field, and instead of having those wells, you now have like a little peak, actually. And your electron will form on the other side of this peak, and then it will fall down into the well. So this process gives you 100% internal quantum efficiency. So every photon that actually penetrates the surface will be detected in the sensor. And so these tests, this is showing the 1 minus reflectance of silicon is the black line here. This is quantum efficiency versus wavelength. And so you can see that the QE measurements for a delta dope CCD match pretty well. The deviations over here are from quantum yield. A higher energy photon sometimes will make 2 electrons, and so that changes your efficiency a little bit. And then over here, the turnover is because it depends on the thickness of the CCD. If it's thin enough, as you go to longer wavelengths, the photon actually just passes entirely through the detector. So now if you look at this in the UV, the efficiency is only 30%. That's not that great. And this trench is basically because silicon is really shiny and it's very reflective in the UV. So then you can do what is a very basic optical solution that has been around for hundreds of years, is you have an anti-reflection coating. This might be the first time I've given this talk where I don't actually need to explain how this works. But you can put a single layer or multiple layers of something on, and you're basically destructively interfering the reflection, and you get more transmission into the surface. So my earliest graduate work was actually designing anti-reflection coatings for delta dope CCDs, and we showed that it works in the UV, which seems obvious, but at the time we weren't sure if it was going to work. And so this is single layers of hafnium oxide, aluminum oxide, and mag fluoride. And then we're just contrasting with the GalX detectors. So this is the far UV microchannel plate and near UV microchannel plate. So just by changing the type of detector and having this very basic coating on it, you can get a 5 times improvement in the throughput of your system. And then these were like really basic single layers, and then the group kind of decided to make things even more interesting because you can do a more complicated anti-reflection coating. In the visible, there are anti-reflection coatings that are hundreds of layers thick. And in the UV, of course, you're challenged by the materials that you can use because things become absorbing in the UV. But you can do multi-layer stacks like this. So the solid line is just the silicon without any coating. And then this purple line here is a single layer, and then a 3-layer stack, and then a 5-layer stack. And so depending on what wavelength you're shooting for, you can adjust your materials and their thickness and really target a particular bandpass and get QEs of above 80% in the UV. Then the other thing that you can do, so this figure here, if you delta dope a CCD and you want to use it in ultraviolet, that's great, but you also have a lot of visible wavelength throughput. And that's one concern with using these is called red leak, where you're looking at a UV target, but you're going to get a bunch of visible wavelength photons at the same time. So you want to be able to filter those out. And you can basically put an integrated filter on the surface of the CCD itself, which is what's shown here, where you have, instead of all dielectric layers, you do a layer of aluminum or some other metal in between, and acts like sort of a pseudo Fabry-Perot, and just picks out the wavelengths that you want, and then has rejection on the order of like 10 to the minus 4 in the visible. And then since these kind of improvements, we've also been working on a project more recently, which is to try and do a different filters in different parts of the detector. So all the stuff that I previously showed you, it's like covering the entire detector with a single anti-reflection coating. But you can imagine a situation where you maybe want different materials in different regions of the detector, if it's going to be in a spectrograph and one wavelength will only hit one part of the surface. So we've been working on these UV optimized block filters where you have a sensor and then part of the sensor has one thickness of an anti-reflection coating, the other part of the sensor has another thickness. This is a picture of it after the coatings were applied. And you can see even in the visible, the reflectance is a little different. This is a picture at room temperature of some of the early results that we're getting, but this figure is showing the quantum efficiency versus wavelength of the different regions of the detector. And so one of my other graduate students, Afaq Khan, is working on doing the testing of these devices. And eventually what we'd like to do is to do like a ramped filter where it's a continuously varying filter across the surface. Okay, so I've talked about the technology that's made UV missions possible, and I'm going to talk a little bit about the missions that I'm working on and kind of my own science interest in the UV. And I'm going to keep this like very basic, and I'm also excited because this is the first time that I can include all the ZMAX like optical paths and have people not think it's just like a bunch of junk. So the big questions that I'm interested in, I feel like these questions might seem really simple, but they're like all simple questions. They're like really difficult to answer. So I'm really interested in knowing, why do galaxies look the way that they do? And how do those galaxies interact with their environments? And one way to think about this, so this image is from Galaxy Zoo, which is this citizen science project to identify types of galaxies. And you can look at galaxies and they have this huge variety of shapes and sizes and colors and like star forming histories. And some of them are really beautiful and others are these just like boring blobs of old stars. And I think part of why galaxies look the way they do is related to the environments that they're in and what happens to the galaxies as they like move through those environments. And so this is an artist representation of that circum-galactic medium that I was talking about before, where you have the galaxy just in this little center part, but the kind of galaxy halo is way bigger than just the visible bright light galaxy itself. And you have a accreting gas coming in from farther out in space. This is like probably primordial hydrogen that was formed in the Big Bang that is only just now falling into a galaxy. But then you also get outflows from supernova that go off within the galaxy, some of which falls back down again on the galaxy. And so there's this really complicated dance of like hot gas that is, some of which is being ejected, some of which is still falling in, and then colder gas that's coming in from farther out. If your galaxy is in a cluster, this becomes even more complicated because there's just a lot more stuff going on. And what's interesting is that out of all the gas around all these galaxies, barely any of it is ever going to become a star. Most of it isn't ever really turned into stars. So if you're only looking at stars, you're really missing the full picture of what's happening. So one of the missions, which is designed to kind of observe the halos of galaxies in nearby galaxies, is called Aspera. The PI is Carlos Vargas, who at the time that we put this in, he was my postdoc, and then now he's a faculty member here, which is I feel really good about. The idea of Aspera is to observe the circum-galactic medium of nearby galaxies in oxygen-6, one of those emission lines that was in the figure that I showed way at the beginning. We have these simulations of what we think the kind of morphology of oxygen-6 emission might be around galaxies. So in this figure, the galaxy is actually in the center here. I mean, it's been taken out because it's way brighter than the surroundings. So this like weird hamburger thing in the middle is the galaxy, and you're viewing the galaxy from edge on. And then you can see there are all these like filamentary structures coming in, which is pretty complicated if you watch. People usually make movies out of these simulations, and there'll be like big explosions from the galaxy as like stars explode, and then the gas will kind of coalesce into filaments and then come back down again. And so we're kind of seeing the aftermath of all of that. But we've tried to look for this emission with FUSE, a telescope that was launched in the early 2000s. In just a couple of galaxies, FUSE looked at where these points are labeled A, B, and then 1, 2, 3, around 2 nearby edge-on galaxies. And it found emission in some places in A and B, but not in others. And we think that this might just be an effect of like chance, because it's just looking at a single point. It's not looking at the entire like halo. If your telescope is looking at point beta here, you're not going to get any signal, whereas if you were lucky and you hit alpha, you do get signal. So part of the motivation for the Aspera design is to be able to cover this entire view with spectroscopy. So you're basically having two dimensions of in X and Y, and then one dimension of wavelength, and you're actually able to get a full view of the morphology. So Aspera is really fantastic for a number of reasons. It is almost entirely, it's going to be basically the entire instrument will be built here at Arizona. It's a collaboration of a bunch of really incredible Arizona people. So Carlos is the PI, and I'm the deputy PI, and we have an excellent science and technical team. Daewoo is one of our optics leads. And then a bunch of grad students are involved in it. Aspera is this class of missions from NASA that's called a Pioneers mission, which they only started in 2020. It's $20 million missions, which seems like a lot of money. It is a lot of money. But something like JWST is like a $10 billion mission. The next classes of missions, if you're interested in building space missions, I also have a lot of things to say about it. But the classes of missions are like 150 million is a small explorer, 300 million is a medium explorer, 1 billion is a probe, and then you have flagships, which are even bigger. And below 150, there wasn't really a lot available if you wanted to do like a CubeSat or a SmallSat. And so NASA created this Pioneers program for $20 million SmallSat missions. So this was originally proposed in 2019 just to get funding for a concept study, and it wasn't selected, and we reformulated things, actually mostly with the work of Han Chung, who's another, was also my postdoc and now is an astronomer in the department. And he came up with a better optical design than what we had used previously, so it was selected in January of 2021, and now we're in phase B of our development. And the optical design is inspired by the FUSE telescope. So the FUSE telescope had 4 channels, and each channel consisted of basically a roll-in circle spectrograph, where you have an off-axis parabola, a slit, a grating with power on it, and then a detector, and that's it. And the FUSE had this design because it could only really afford 2 surfaces, because each surface cost it 40% throughput. We're doing this because actually it's a very clever design, and the grading technology has improved enough that whereas FUSE only had a single point that it would look at, we can actually observe a slit with really good resolution. So we're observing from 103 to 104 nanometers with a spectral resolution of 2000, a spatial resolution of 45 arc seconds, and the slits are 60 arc minutes long, 30 arc seconds wide. And so we have 2 channels, whereas FUSE had 4. So you can see each of these are the off-axis parabola, it's the primary, and then the gratings are here, and then there's a single detector that they share. And this has also been a really good project, partly because it's only $20 million, so from the perspective of NASA, that's they're not as worried about the telescope not working as they are for like a flagship or a bigger mission. The bigger the mission, the less willing NASA is to allow like early career people or students to work on it, because they don't want things to get messed up. But for something of this size, it's a really great opportunity for students to be involved and to learn the basics of like space mission design, integration and testing, and lots of other stuff. So all of the grad students are involved in different aspects of the Aspera design, which is really fantastic.
What is the physical scale of that?
So this is about this big. It's tiny. The entire spacecraft and everything is about the size of like a mini fridge. And we have a 3D printed full-scale version of it in the lab that you can just like pick up and carry around. I should have brought it. Oh yeah, and the other thing is like you'd really be surprised at how little $20 million buys you when you're sending it into space. And we don't even have to pay to get it into space. I'm going to show you how the kind of mock observation works. Basically, we have a couple of slits that will move across the field and build up the signal over time. The telescope itself, each channel is very small. So the Fuse telescope, I think it was like 40 centimeters by 40 centimeters, like for each channel for the primary mirror. And for Aspera, it's about 5 centimeters. But our performance is almost the same because everything has improved a lot. But we still have to look at each target, each pointing we're doing for 2 days, and then we'll add up over time about 14 days worth of observations in order to look at a single galaxy. So in terms of our observing plan, we're only planning to look at 10 galaxies. We have a 9-month mission lifetime. If it's still working at the end of the 9 months, then NASA will probably give us more money that we can keep going. But part of the requirement for this type of mission was that it only lasts 5 years. So this is our schedule. We're anticipating a launch in 2025, and incredibly, we're still on track for that. I'm like really excited about it. We had our PDR, preliminary design review, earlier in the year. And now we're working towards the next kind of milestone is a critical design review. And then this phases C and D is when you actually build the thing, put the payload together, and then you send it to the spacecraft provider. The spacecraft is being provided by Space Flight Labs, which is at the University of Toronto. Then they'll integrate it into the spacecraft. Then they send it to the launch vehicle, and it gets integrated into the launch vehicle, and then it gets launched. And then we have this 9-month phase E, which is when you actually do the observations and get all the data back. So if everything goes well, 2025 will be a really thrilling year for us. And one thing that I think is kind of interesting is Hamden also made this beautiful chart showing how Aspera compares to other mission concepts. So this is a graph showing the integrated exposure time versus the sensitivity that we can observe in that exposure time. So like how deep can we go? What's the faintest thing that we can observe with a signal to noise of 3 or 5, sorry. And then we're comparing different missions. So LUVOIR, these are different versions of that large UV optical infrared telescope that I mentioned. LUVOIR B, I think, is like a 4-meter primary. LUVOIR A was like 10 meters. CETUS is a different probe class mission concept. So this is a $1 billion mission with like a 1-meter telescope. And then FUSE, that early telescope that Aspera was inspired by. And then Aspera is the blue line. And one thing you'll think is kind of weird is like LUVOIR B and A are these gigantic telescopes, and their limiting sensitivity for the same exposure time is like an order of magnitude greater or more than Aspera. And Aspera is this teeny tiny small refrigerator-sized telescope. So like, what's up with that? And the reason why, of course, is here you can see the resolution elements for each of these missions. So LUVOIR is so gigantic. The resolution elements are all going to be really tiny because that's the way that it works. If you have a bigger telescope, your field of view is smaller, whereas Aspera has a tiny telescope and a big field of view and has huge resolution elements. You could, of course, bin the resolution elements from your LUVOIR observations and get down to better sensitivity, but I show this because partly there's like a class of people in astronomy who are really into flagships. Flagships bring in a lot of money for astrophysics. They like employ a lot of people, and so I get why people are into flagships. But I also think it makes for kind of lazy science where you think, well, I need to wait for a flagship before I can observe the CGM or before I can answer my questions. And I feel like, yes, you can probably answer any question if you have a big enough telescope, like sure. But I think that if you ask interesting pointed questions, you can answer them now using a small telescope, and you don't have to wait until I have a figure way at the end. But like LUVOIR, if it gets launched, it's going to be in like optimistically 2045. Not optimistically, it'll never happen. And like so so I feel like you should just do the small thing now that is interesting and will get you part of the way to understanding the universe instead of hoping that a future flagship is going to save you. And so that's partly why I'm really excited about the fact that the Pioneers class of missions exists at all. Because you can have like a pointed question, get money from NASA, build it in 5 years, and then answer your question. Okay, so I'm going to shift to a different telescope that I've been working on for a long time, which is also observing kind of the same science, trying to look at the halos of galaxies. Instead of looking at nearby galaxies, we're looking at slightly more distant galaxies, but still in the UV and in close to space. So this is actually a balloon-borne mission. It's called the Faint Intergalactic Medium Redshifted Emission Balloon, which we call it Fireball for short, which is a good name for a telescope. People seem to like it, although it also gives the implication that like it could blow up at any moment. There's nothing really volatile on it, so it won't. But this is PI'd out of Caltech by Chris Martin. And this, like the Pioneers mission, is also really good in that it's an excellent training ground for early career scientists, for grad students, to like be involved in important flight hardware. And as I've like moved up in my career, I feel like training new people to come after you is one of the most important things that you can do. And so it's really important to me that the missions I work on do that. So Fireball observes at around 2,000 angstroms, 200 nanometers. And it turns out that if you go high enough in the atmosphere, there's a window of atmospheric transmission between oxygen absorption at around 40 kilometers. So we are observing Lyman alpha that has been redshifted into this bandpass. There's nothing special about the redshift that we're observing at. It's just because that's where the balloon window is. The higher you go, actually, the bigger this window gets. So NASA is experimenting with bigger balloons that can take you up to 60 kilometers, and that you'll have like an even wider bandpass in the near UV that you could observe in. So Fireball 2 is the current version that we're working on, and so it has like a little bit of a wonky optical design because we're using 2 large mirrors that are left over from the first version of Fireball. So we have a 1.2 meter flat siderostat that helps pick out the field of view, and then a 1 meter parabola that's f2.5, and then a spectrograph, which is all enclosed in a tank down here. So we have a 2 optic field corrector, which I'll get to later, and then a spectrograph that basically consists of folding flats and spherical Schmidt mirrors. So you have the input beam from a slit mask, a Schmidt, a folding flat, the grating, another folding flat, another Schmidt, and then the detector here. So this actually has a lot of optical surfaces, which can be somewhat challenging, especially for like alignment. And we flew in 2018 from a town called Fort Sumner, New Mexico. Has anyone here been to Fort Sumner? What do you think of Fort Sumner? Yeah, so Fort Sumner is a town of about 800 people. They do balloon launches from there because one time in the 1960s, when they were looking for places to do balloon launches, they sent people to different parts of the country to check the weather, to like test the weather every day and see what the low-level winds were, the surface winds over time. And that the year that they sent someone to Fort Sumner was an anomalously good weather year, it turns out. That's why we're there. And so the weather actually isn't that great, and it's hard to launch balloons from there, and so you end up spending like 10 weeks in this tiny town. There used to be 4 restaurants, now there are 2 restaurants. It's close to Roswell, and the U.S. government has been launching balloons from this part of New Mexico since like the 50s. Before it was NASA, it was like classified projects. And people have been seeing aliens in Roswell since like the 1950s. If you go to the Alien Research Center, it's the Extraterrestrial Research Center, sorry. They have like pieces of balloons and pieces of like mylar from the payloads. But you send the balloon up, it floats around for like a day, it comes back down and lands randomly because you can't control where it comes down. And they send a team of people out to go get it. And back when they were sending classified like payloads up, there would be a bunch of government men that would show up on the doorstep of some farmer's land and be like, hey, we dropped something in your field. We need to go get it, but you can't look at it, and here's a briefcase full of cash. And so I feel like, of course, people think that it's aliens, but it's not. It's just classified science. Now they don't bring a briefcase of cash. They write them a check. And so actually in 2020 during the pandemic, so Tucson is like down over here somewhere, and I drove to New Jersey to see my parents because I didn't want to fly. And so this is like when we didn't know anything about COVID. And so the other thing that Fort Sumner is known for is the Billy the Kid Museum. And so I was like, well, I'm close to Fort Sumner. I might as well drive through it. So this is me in 2020 outside of the Billy the Kid Museum. So we flew in 2018 and we were supposed to fly again in 2020, but at least I went to Fort Sumner that year. So our flight in 2018 was after a lot of heartache. We had actually gone out for 10 weeks in 2017, and the weather was so bad that year that basically no balloons flew, because that was the year there was all these hurricanes that went through like Texas and the Gulf, and there was too much moisture and we couldn't launch. 2018, we actually had good weather, so this is the balloon launch. It's full of helium. And then we're set up on this old airport. And then once the balloon is, they don't fill it up all the way on the ground, because as it ascends, it gets bigger. They let us go. And then Fireball is hanging from a crane. The crane is called Big Bill. Big Bill like drives around to keep everything vertical so that there's no big shocks when the balloon actually straightens out. And the balloon, the chain between the payload and the balloon is so long that you need the surface winds and the low-level winds that are a couple hundred feet off the ground to be moving in the same direction to just make sure that no disasters happen. This was actually a really nice launch. It happened at about 10:30 in the morning. You can see the airport that we work out of, and also that there is nothing here. We had some GoPros on the telescope, and you can see like the shadow of the balloon. And it takes several hours for the balloon to ascend to the float altitude. We're trying to get to about 130,000 feet. And over the course of that ascent, the balloon expands, the helium in the balloon expands. So this is our downward-looking GoPro once it's pretty high up. And then we have these doors that open when we're ready to make observations, and you can see the balloon is way bigger here. And then after the flight is over, there's an explosive charge between the balloon and the parachute that severs the connection, and then they both like fall from whatever altitude they're at. You go find it, bring a crane, and maybe build a road. This was actually a really easy recovery also. It just like falls somewhere. And one thing that they're very concerned about is that it doesn't fall over like a populated area, so they do all this like analysis of various trajectories before they do the launch to make sure that they can bring it down in a safe place. And then this was some, but not all of the team. About half the team was sleeping when we took this picture, because you spend all day getting, like the whole previous night getting it ready. It launches, and then a couple hours later you spend all night observing. So it's really taxing. And so this picture was taken the evening of the launch. So this is the balloon, and here's Fireball here. This picture was taken by a guy who works at Los Alamos, and he usually does bird photography, nature photography. And his mom called him. I don't know if your moms ever do this, but my mom will call me and be like, hey, there's something weird in the sky. My mom lives in New Jersey, so it's annoying because I can't even be like, oh, let me look. Anyway, his mom also lives in Santa Fe, so he was like, oh, it's probably a balloon, because science people in New Mexico know that a certain time of year they're doing balloon launches, so a weird thing in the sky is probably a balloon. So he grabbed his camera and ran out and took this picture and then posted it on the internet. And then somebody that I know saw it and was like, I think this is your telescope, and it was. So this picture I have in my office. It's also at my house. It's the background of my computer screen. And it'll probably be on my grave. But I like this. I love this picture. It's really beautiful because I worked on Fireball since basically 2008, and eventually was leading the team that launched it. And I also hate this picture because the balloons are supposed to be spherical when they're fully inflated, and this balloon is not. It is shaped like a teardrop, and that's because there's a hole in it. And there was a hole in the launch before us, and there was a hole in the next two launches after us, and the balloon people were putting too much tension on the balloons when they were filling them, and it was creating like small ruptures that when the balloon actually expands, it creates a hole, and it loses altitude much faster than it's supposed to, and so we need an altitude that's very high to do our observations, and it was too low. We didn't get any good data, and not only that, but there was a tremendous amount of scattered light from the balloon itself.
How high was it in this picture?
So in this picture, it's probably 115,000 feet.
Is that higher than what it did to work?
So it went up to 130,000 feet, and then when the sun sets, the balloon will fall a little bit because it cools off. And we actually have ballast that you can release at sunset to try and drive it up further. So we should have ended up around 128,000 feet. But at sunset, it had been dropping a little bit over the course of the day, but nothing that like drew our attention. But then at sunset, it started dropping a lot. We released the ballast and it didn't do anything, and it kept going. So this picture was taken around 7 p.m. By then, it was at 115 or 118,000 feet. And then when we realized what was happening at 9 p.m., it was at 105,000 feet. And actually, as it kept falling, it's moving through different layers of the atmosphere. That is, the wind is different. And so the trajectory that we had originally planned is no longer valid, which means that it could end up like over Albuquerque, where you can't bring it down. Or it could end up, this was unlikely, but like if the balloon is heading to Mexico, that is bad. And you have to like bring it down. And even bringing it down at the nighttime is really rough on the payload because the winds are much stronger than they are in the morning when things tend to be calm. So we had to cut it down at around 1 a.m. because it was over a favorable area that would be easy to reach and didn't have a lot of people. But yeah, so this picture is like an indicator that there is a problem. But of course, I didn't get this until way later. And we didn't really know. Like I remember reading out, there's a GPS on the payload, and I remember reading out the altitudes and being like, oh, this is weird. But like, I had been up for like 36 hours and it was hard to interpret it, exactly what was happening. And then the balloon people are like, oh, we think that there's a hole. And so we tried to just observe, like we kept switching. We had like a whole, observing plan, and like, we're going to look at this target and then we're going to switch to this target, and we had everything planned out. And then we just like threw it all out and we're like, okay, like what's the brightest UV source nearby? We can switch to the Andromeda galaxy. We can switch to this like UV bright star. We just tried to salvage something, but by then we were way too low. So one of the things that we've been working on is a way to mitigate stray light. So one of the issues that we had, which seems really obvious in retrospect, but one of the issues we had is that the deformation of the balloon causes these like caustics to form at the bottom of the balloon that end up being really bright. And there's a parasitic path that we hadn't blocked, basically from the top of the doors, looking at parts of the balloon, and then it would go through the hole in the siderostat. It like skips the primary entirely, bounces off some things inside the spectrograph tank, and then ended up hitting part of the detector. So we had all this, we had like 1,000 times more scattered light than we had planned on having. So one project since then that Trent Brundle, who is sitting in the audience over here, has been working on is doing a like very comprehensive stray light analysis and mitigation strategy for our next flight. So in addition to having a baffle across the doors that blocks part of the view from the balloon, we've also implemented a number of other baffles. So the blue is showing where there were baffles in the 2018 launch, and then the red is all the new improved baffling strategy. So we're feeling good about being able to at least alleviate the issue of scattered light off of the balloon or off of whatever. I mean, the other problem was that, if you'll notice, it was like a very close to full moon that night, and so the balloon reflected a bunch of moonlight and then directed it downward. You can even see in this picture how bright the like edge of the balloon is, and so in addition to the altitude, the kind of huge amount of scattered light was a big problem for us.
And run all of your own recovery, or is that about some subcontract?
So the balloon launches and the recovery are done by the NASA balloon people. It's the Columbia Scientific Ballooning Facility, which is operated under a contract with, I think Northrop Grumman does it right now. And that we don't pay for. Like, we have a NASA grant to build the telescope, and then the balloon, the like launch and recovery is like part of the process. So we had been planning for a 2020 launch. After we recovered it in 2018, we needed to fix a couple of things and realign things. So here we are working at Columbia in New York City in February of 2020. We're like so naive. We don't know what's coming for us. And COVID slowed things down a lot. We've been redoing optical alignments. We had restarted stuff mostly by 2021. I want to highlight Simran Argwal here And here, who's one of my other students who's doing the optical alignment. In this picture, you'll see the 2 optic field corrector. And this has been a really challenging optic. It actually partly broke on the landing in 2018, along with the 2 large optics also got banged around. But this optic, the large surface here got one of the bonds broke, and so we had to rebond it, and then that alignment failed when we were trying to ship it to Fort Sumner. So it is now in Steward, and we're gonna realign it in November with a CGH, a computer-generated hologram from AOM. And I'm really excited about that because I think it's going to be a really interesting process. And then the idea is that we'll put everything back together and then go out to Fort Sumner in 2023 and hopefully have a balloon without a hole in it. Although they did figure out why those holes were happening, so I think we'll be fine. So then in the last little bit of time that I have, I'm just going to talk about another mission, which is unfortunately still a concept and not a real thing. But this is a totally different science case. This mission is designed to look at molecular clouds, which is where stars are formed in our galaxy. It's called Hyperion. This is a larger class of mission than Aspera, for example. So this is a medium explorer. It's a $300 million proposal. And I worked on it with JPL and Ball Aerospace, plus an extensive science team, lots of people at Arizona. And this is actually the second time that I've put this proposal in. I put in a smaller version in 2019. And I feel like all the missions, well, Aspera hasn't broken my heart yet, but Fireball, the balloon hole definitely did. And with this, we put it in 2021. They give you a opportunity to respond to potential major weaknesses. And they gave us 2 potential major weaknesses. And normally mission teams get like 10 to 15. And so we were feeling like, oh, they love our mission. This is like really good. And then in August, we found out that even though we had no major weaknesses in the actual review, and we were listed as category 1, which is the highest category possible, we were not selected because they decided to go with other science topics. And I'm like sad and kind of sore about it. But I'm currently deciding whether to reformulate it for another round. The problem with these types of missions is that you can't propose them every year. For the medium explorer call, there's 2 opportunities a decade. So I could wait 5 years and repropose this. For the small explorer calls, it's also 2 a decade. The next one will be in 2 years, and so I could try and shrink it back down to $150 million. So I'm still deciding what to do. But the idea behind Hyperion is answering different questions than Fireball or Aspera. It's trying to understand how a star forms and what the star does to the environment around it once it's formed. And so Hyperion is looking at totally different signatures than Aspera or Fireball. We're actually looking at molecular hydrogen itself, which was the tracer that was found in those very early UV telescopes. We're trying to understand how molecular hydrogen forms at the surface of molecular clouds and how it gets destroyed, and then how the stars that form in those molecular clouds actually destroy their birth clouds, and then how planet-forming disks, which are very rich in molecular hydrogen, actually get destroyed by the star that they're orbiting around. And we're looking at H2, which is the dominant component of molecular clouds. Any beautiful picture of space that you see that is not a galaxy is probably a molecular cloud. And that's what makes it look so nice, because they're these like really interesting, complicated places with lots of different densities. And you have something like this. This is the Eagle Nebula. There's a bunch of stars. The new super UV bright stars here, and they're kind of sculpting and changing the cloud. Molecular clouds you can think of as if they're kind of onions. They have different layers. So the outermost layer is going to be mostly atomic. And then as you go deeper into the cloud, the outer layers kind of shield the inner layers from the radiation from really bright stars. And then you'll get more complicated molecules that form, and eventually you can have stars form in these denser parts of the clouds. So Hyperion is looking at the surface of the cloud, basically the boundary between atomic and molecular hydrogen, and H2 has a really rich UV fluorescent spectrum. Some astronomers will claim that H2 doesn't emit at all, which is why they don't observe it, but that's wrong. It just emits in the UV, which is everybody's least favorite wavelength. But it emits in the UV because you can excite the molecule itself, and it'll have this really rich, complicated spectrum of emission lines, which depend both on the ionizing, the energy source, and the state of the molecule itself. And if you have a high enough resolution telescope, you can actually pick out all these hundreds of lines. You can figure out how the molecules are moving, and a bunch of other characteristics of the gas. So Hyperion has basically a single instrument, a spectrograph that has two different resolutions, a resolution of 50,000 and then a resolution of 10,000. The optical design is interesting because we were trying to have only one grating for the entire system. Because typically with a high resolution spectrograph, you'll have two gratings. You have a shell and then a cross disperser, but each of those gratings costs you a bunch of efficiency. And we were trying to match the efficiency of basically HST as kind of a benchmark so that we wouldn't get a weakness about efficiency. So we have a primary mirror that's 48 centimeters, a secondary. We have a couple of relay optics just to improve the field of view. Our slit is very long. It's 70 arc minutes long. And then a spectrograph optics, a grating, an extremely large M6 mirror because the resolution is so high and the slit length is so long. And then a little fold mirror, and then a 4 detector array for the focal plane array. So this optical design and putting it into space costs $300 million. If we do the smaller version, we'll probably have to adjust something in order to save a little bit of money. But I think it's important to work on and to keep promoting other UV missions because eventually there's going to be a big gap in good UV access. So this figure is from the Astronomy Decadal, which came out last year. And they recommended, here's the IROUV flagship, UV at the end, but not for launch until 2045. So NASA just launched JWST. They're working on another flagship called Roman that's going to launch towards the end of the 20s. And then they have some probe missions, the 1 billion class missions, but they think that we need more technology development before we launch the large UV optical infrared, which is fine. But HST is going to end, and right now HST is the primary way that astronomers can observe in the ultraviolet. And HST, because we don't have the space shuttle to do servicing missions anymore, one day the gyroscopes probably are what's going to fail, and it won't be able to point. And then we'll have this huge gap here between the end of HST and when there's more UV access to space. So I feel like encouraging smaller missions like Aspera or other UV Pioneers concepts and pushing forward with these other methods of getting UV telescopes into space are really important. So I'll end here. I think UV astrophysics has benefited tremendously from all the technical improvements in gratings, in detectors, in coatings, and that in a post-Hubble era, it doesn't need to be a big blank spot in the timeline. It can be exciting, fruitful, and full of discoveries. And just as a sort of to end on, if any of you out here are interested in like knowing how to develop missions, please talk to me about it. It's usually something that is like hidden because it's a lot of money, gives you a lot of power. So the people that know how to do it typically don't want to share that. But like, I want to share it. So talk to me about it. Writing these proposals is like my like most favorite thing to do. So with that, I'll end. Thank you so much.